We are going to start the lecture by Dr. Kaczmarek. As I see from this sort of exercise and the presentation of those backdoors to the complicated theory.
Yeah, right. So today I will not make really the exercise, but I will explain how you should do the exercise. So the idea is that you take really a lattice program, a program for SU3 pure gauge theory. So this program I wrote some, I don't know, 15 years ago or so. You can download this program on this web page there. What you need is a C++ compiler. The best would be a GNU C++ compiler. So that should work at least under Linux and also on a Mac. If you have a Windows machine, then just go to some of your colleagues. Work together with them. If it doesn't compile, so you have to download it. It's a tar file, unpack it, and then just type mate, so then it will compile. If it doesn't compile, then talk to me and I will to set it up. I have to explain you a bit how this works. So what this heat bath and over-relaxation algorithms are. So I will go a bit into the details later on, and then we can discuss what we will do with this exercise. And then, well, this afternoon there are no lectures. In principle, you have time to work on that.
Yeah.
So if you are fast, you can just, right, that's really your homework. So if you are fast, then you can choose some parameters and let your computer run for the whole afternoon and night. And then tomorrow we will discuss your results and see what kind of critical temperature you will get for SU3 pure gauge theory. Okay, I will go a bit into the details later on, but let's start with another topic which I already discussed a bit yesterday, but which I think is very important, and I will go a bit more into the details, and that's the continuum limit. So yesterday I showed a lot of results that we obtained on finite lattices, and where we performed the continuum extrapolation, and then I showed you mainly some continuum extrapolated results. But the big question is, can we really trust this continuum extrapolation? So is it obvious that when we take some lattice results and perform the continuum extrapolation, that we really get the correct physics? And this is a really non-trivial question, and I will go a bit into the details on that. So the idea is to take the continuum limit, so the limit a to 0, at, let's say, a fixed temperature, and I told you temperature is 1 over a times the temporal extent of the lattice. Or you want to keep, let's say, quark mass fixed, so you want to keep m cubed in units of a fixed. And I already told you that this corresponds to taking the limit of the bare coupling G to 0, but I didn't really explain why it is so. I explained it a bit, but I will go a bit more into the details. So the only parameter that we have, at least in a pure gauge theory, is this bare coupling G, which is not at all a physical quantity. It's just a parameter that you put into your action, then you run your simulation and get some result. But then you have to relate it somehow to a lattice space in A, so by comparing to a physical quantity, for instance, calculating, let's say, a rho mass and compare to the physical result. And this way you can, in principle, determine the lattice space. But then if you want to change the lattice spacing, go to some other, for instance, go closer to the continuum limit, so you make the A smaller, or you want to make the A smaller and the NT larger at a fixed temperature, then you really have to understand how the lattice spacing changes with the coupling, or how you have to change the coupling in order to change the lattice spacing to get the same temperature, for instance. And sure.
I mean, that is LQA, because this is dimensionless.
Well, this is right. This is dimensionless.
Multiply and divided by n tau. This will be nq over t.
Exactly. Let's do it like that. So you want to keep m over t fixed. Let's say. Okay. Well, but let's forget about m. Let's just talk about temperature. That's already fair enough. Okay. So then I said that there is something which is called the beta function, beta of g, which is, today I make the sign correct, I hope. So this is minus a times d, divided like this, dg, dA. So that relates the lattice spacing to the coupling, and this you can, for small coupling, calculate in a weak coupling expansion, and then you get minus B0 g to the power 3 minus B1 g to the power 5, and then plus higher order terms g to the power 7. So that's the beta function. And if we plot this beta function, maybe let's do it here. Let's say we plot beta of g with respect to the coupling. Then what you see is that for small coupling this is negative, and it should go to 0 in the limit of g to 0. Okay? And this is very important, because this says that here at g equals 0, you have what is called an ultraviolet fixed point. And to have an UV fixed point at some coupling, it could also be not at 0 but at some other g, is extremely important to take the continuum limit in a controlled way. What this means is also, or what you in principle also have to do, but which I cannot explain in that detail here, you have to renormalize all your quantities. So when you tune this A of G, let's write it here also, A of G, to 0, in principle you have to renormalize all your quantities. So you have to renormalize also the coupling. So this renormalization theory leads to also renormalized couplings, renormalized masses, and all your observables that you want to calculate, you have to renormalize in a good way, which means that you calculate these renormalized quantities then on a line of constant physics by changing the lattice spacing according to this RG function. Okay. And what are the important things? So one important thing is that any correlation length must diverge so let's call the divergent length psi over A, which you, for example, can estimate by calculating the mass. So 1 over some normalized mass times A, that must diverge. That must go to infinity because A has to go to 0 in the continuum. Okay? But what does it mean that a correlation length diverges? Do you have any idea? what does it mean in terms of, if you think of phase transitions?
Second order.
Right? So this means that we need a second order transition to let the correlation length diverge. And what does a second order transition imply? What kind of behavior do you expect for a second order phase transition? Here.
So you ask about observables or what?
Well,
Ask for
I want to argue that you need, or that you have universality at a second order transition.
So if he will answer,
Okay?
what universal? Okay, fantastic.
Well, so a second order transition always implies universality. So that means that critical properties at this second order transition become universal. And they are only related to the underlying symmetries of your system. Okay? This second order transition that I'm talking here about in principle is not a really physical transition, but it's a transition in the limit when you set a to 0, then you get universality in this limit, so in the continuum limit. So this also means that if you have universality, this means that you get the same continuum limit for different discretizations of your theory, at least if the underlying symmetries are the correct symmetries. Okay? So if you think of SU3 pure gauge theory, then of course you need SU3 elements, you need a gauge theory, and you need to have local gauge invariants of this theory. But then you just can discretize your theory no matter what you want to do. You can take a standard Wilson gauge action, you can use some very highly improved action, whatever you want. You cannot only take an isotropic lattice, you can make it anisotropic, well, whatever you like. Okay? As long as your symmetries, underlying symmetries are correct, you should get the same continuum limit, whatever you do. Okay? What else do we need? Well, divergencies. So as I already said, all the bare couplings, so like G and all the masses, they diverge in the continuum limit. So what you have to do, you have to renormalize, and then you can prove, at least for this theory, that it's renormalizable. And that means that if you express your observables in terms of renormalized quantities, so in terms of a renormalized coupling, renormalized quark mass, or whatsoever, then this renormalizability means that if you take the limit in a controlled way, where you take the limit of A times, let's say, a mass to 0, and you express your observables in terms of renormalized parameters, renormalized couplings, renormalized masses, and so on, then this limit exists. and then you can prove. But what is important to have all these things is that you have a UV fixed point in this beta function. UV fixed point means that this curve comes from below to 0. You need 0 here because that means you get a second order transition. That is.
Sorry?
Yeah.
This tau under the limit, what is that? It's observable, yes?
So you express the observable in terms of renormalized quantities and take the limit A, this is an A times, let's say, mass to 0.
Mass of what?
Let's say of a quark mass. Okay, or okay. Well, this UV fixed point is here at 0, and coupling 0 also means that A to 0 corresponds to G to 0. Okay? If it would be somewhere else, then you would have to take the continuum limit at a finite coupling. And this, of course, comes because you have asymptotic freedom here in QCD, because this beta function here is the same beta function, at least in leading order, than for the renormalized coupling. Okay. So for the renormalized coupling, this would read like this. Let's do it here. So then you would have a beta function, beta g of r, which is minus r d gr dr. So this dictates the dependence of the running coupling, the renormalized coupling with r, and then you get a running coupling, gr of r, which also goes to 0 for r going to 0. Okay. So this here leads to asymptotic freedom. In QCD. Okay? Because the beta function here is the same, it has the same parameters, B0, B1, they are universal, so they are the same in all RG functions. Higher order terms can be different, but that they can depend, for instance, on the discretization of it. Okay. Yeah, I think that's I think all that I wanted to say about the continuum limit. But this really shows that all that we do on the lattice and then taking the continuum limit gives us the correct physics and also independent how we discretize the theory, as long as we perform the continuum limit in a controlled way. One could have a whole lecture about renormalization group theory, but this is just the basic ideas behind it. Okay. Any questions about this? This would be, for instance, much different in other theories. So for instance, if you think of phi to the 4 theory, there one doesn't have a UV fixed point. And this also means that there is no non-trivial continuum limit in the phi to the 4 theory. So you can calculate the phi to the 4 theory on the lattice, and you can also perform the continuum extrapolation. But what you would get in the phi to the 4 theory is a trivial continuum limit. So you get a non-interacting theory in the continuum. And this is really different here. You really get an interacting theory. Okay. Any questions?
Maybe you could explain, because usually on the lattice you are not going with A to 0, but you are going with n tau to infinity, or n tau large, okay? So how it is related then?
Well, this is related to this here, so we want to keep the temperature fixed. So if we take the limit A to 0, then we have to take the limit NT to infinity. Or if we want to let's say, make a factor 2 smaller, then we need to take nt a factor 2 larger. That's why we always talk about nt to infinity when we talk about the continuum limit, but this also means a to 0. Okay. Good. So now you know how to discretize at least the pure gauge theory on the lattice, how in principle you perform the continuum limit. But the question is how to do a real lattice calculation. And this I will explain now, well, a bit briefly, but I will explain at least the basic ideas, what we do there. And what we do there is called Monte Carlo integration, which is a statistical integration method. And why we have to do it statistically, I will explain now. And this question came up yesterday already. I think Jakob asked me this question. Why can you not just calculate the partition function z? Okay. So that would be the best thing, of course. Why not just calculate z, or let's say some temperature and some volume? And if we could do that, we would have solved the theory, because we can calculate in principle all quantities which we are interested in, knowing this partition function. But then I argued this doesn't work, and therefore I want to show an example why it doesn't work. And I make it a bit simpler, so I just take an Ising spin model. So there we have much less degrees of freedom. But this already shows that even there it doesn't work. So let's take an Ising model on L to the power d lattice. So L points in discretized in every direction on a d-dimensional space. And the partition function of the Ising model looks like this. So you have spins on each lattice point, so they can either point up or point down. And the partition function is the sum over all these spin configurations. So you can change all the spins, at every point you have to change the spin, and then you sum over all these configurations and weight this with the action or Hamiltonian 1 over k times d times the Hamiltonian, which depends on the spin configuration. Okay, this Hamiltonian is just a Hamiltonian which couples nearest neighbors with the coupling J, and there you couple nearest neighbors Si times A Sj, where I and J are just nearest neighbors on the lattice. Okay, so this is a very simple model, but what we have to do is we have to sum over all these spin configurations, which means that we have 2 degrees of freedom to the power of n such configurations, where n is L to the power of d. And let's just take a small example. So let's fix the dimension to 3. Let's just take 10 spins in each direction. So if I'm not wrong, then I get 2 to the power of 1000 such configurations. So that's 10 to the power of 300, which is quite a big number, where you have no feeling how big it really is. But let's say we have quite a big computer which can do 1 petaflop operations per second. 1 petaflop is 2 to the power 50, which is 10 to the power 15 floating point operations per second. And you need at least 1 floating point operation to do this calculation here, this product of the 2 spins. In principle, you could also do it with integer or binary operations because it's just numbers here, plus or minus 1. So SI plus or minus 1. But nevertheless, we need a bit of computing time here. So you would need 10 to the power 285 seconds on a 1 petaflop computer. A 1 petaflop computer you can buy nowadays for roughly 1.2 million euro or dollar, whatever you want. Zloty, I don't know. So that's still quite expensive. And still you need 10 to the power 285 seconds just to do this calculation of the partition function for 1 temperature and 1 volume. Of course you want to have more temperatures, more volumes, larger lattices and so on. So this is impossible because what is the age of the universe? That is around 4.4 times 10 to the 17 seconds. So that's already quite some time, but this number is very small compared to this number here. And this was just a very simple Ising model where you have 1 degree of freedom per lattice size. For an SU3 theory, you have to integrate over, well, there you have the SU3 matrices on the links, so there, and you have to integrate over SU3, so then you get a large factor here. So that's totally impossible to do. That's why we use statistical integration methods, not to calculate directly the partition function, but to calculate our observables. And this I will now explain in a bit more detail. So the advantage is that, well, if you think of the spin model, then there are only a few configurations, or a relatively small number of configurations, which really give a large contribution to your partition function. And you want to sample these in a statistical way. And what you want to do is you want to calculate some observable. So to calculate this, you have to calculate this integral, 1 over the partition function, times the integral over some field, let's say SU3 field or the Turpin field or whatever. And then you put your operator inside here that depends on this field. And then you have the action e to the minus s. That also depends on the field. In principle, now you have to do this integral here and you have to calculate the partition function. But that's not possible. So what do we do? So first of all, we take this constant here, 1 over z, into here. Just a constant. And then this here, so 1 over z times e to the minus s, that is a probability density, W of phi. So this W of phi is for sure larger than 0. Of course, this must be real to have an interpretation as a probability density. So that's the big problem when you go to finite density, because then this quantity here is no longer real but becomes complex, and that's the reason why we cannot do it for complex chemical potentials, for non-zero chemical potentials. Sorry. What else do we need for a probability density? So we need that the integral d phi over this density is 1. But that's the case because if we just integrate here over e to the minus s phi, then we get z and z over z. So this really defines the probability density. And this we use in our Monte Carlo. So there is no real need to calculate z. And the important thing is that this w of phi is small for many, most of the field configurations phi, and that allows us to do what is called importance sampling. Which means that we try to only sample configurations which give a large weight here to this integral. Okay, so far any questions on this? So the idea is now to generate a finite number of field configurations. So these phis here that are field configurations, so let's say SU3 matrices on the lattice. And we want to generate a finite number or sequence of these field configurations phi for a number L going from 1 to n, let's say. And this n here is what we usually call the statistics in our calculation. So then if these field configurations are distributed according to our probability density W of phi, then we can just sum the result for our observable and of course normalized by 1 over n, sum of L1 to n of our observable O measured on this configurations phi. And that is called importance sampling. Of course, we make an error here, and the error that we make is that we only take a finite number of n here, so this goes as 1 over square root of n. That this goes as 1 over square root of n is because we have a statistical integration method. If you would do a standard integration, numerical integration method, then this error here depends on the dimension even. So even if you do multi-dimensional integrals, it's sometimes good to do Monte Carlo statistical integration. Now the question is, we don't know this W of phi. So the question is, how can we generate a distribution which is distributed according to this W of phi without knowing this? And this is done by a sort of Markov process, where the basic idea I will now First, any questions about this?
Could you maybe, if you remember, the historically tell to students how this method was developed and who did it?
Well, that's a very good question, which I think I cannot answer.
Okay.
Does anyone know?
So I think it was developed in 40s by Wigner,
could be.
by Nobel Prize winner.
Mm.
And that was the time when they had participated in this atomic bomb development in US, and they have had a problem to calculate multidimensional integrals. And that's how they discovered this important subject method to calculate the multidimensional integrals. Important sampling method, which we have mentioned here. So
Right.
I don't know.
Yeah, if you do multi,
people, but I don't remember their name. But I know the people.
if you just calculate multidimensional integrals, then with standard techniques you get here an error which goes like 1 over n to the power of 1 over dimension. So let's say if you do a naive Trapez integration, Gauss integration and so on. So if you make d here very large, then it's hard to get a smaller one. And that's why statistical methods work better there, because there you have the statistical dependence of the error. And that was the reason, I guess, why it was okay. Sorry, more questions?
Under this sum, there is the average, or
Oh, sorry. So you just take these n field configurations that you have, let's say spin configurations, calculate your observables, let's say the magnetization in this Ising model, and sum over these configurations, normalize correctly, and this gives you an estimate. This is of course not equal, but an estimate with some statistical error that you can.
So there are two sums in a sense, because one is over the configurations and one is over the lattice. So
Yeah, exactly. So usually,
this average which you have had means that you have first to average over the lattice.
yeah, exactly. Let's say if you think of magnetization in an Ising model, then this O would be already the sum over the lattice, or the lattice points or spin points of SI. Right. So if you make your volume very large, take a large number, then also this error gets smaller. And okay. So what is such a Markov process? I guess some of you may know all this, but the others may explain this. Because that then brings me to some update algorithms that can be used or is used in the program that I will give you. So Markov process or Markov chain is a stochastic process where you start with one field configuration and you change it into another field configuration, let's say phi 2, and then into phi 3, and so on and so on, in such a way that at least after some time of thermalization, the probability of finding one configuration in a range phi to phi plus a small d phi is given by W of phi d phi. Okay? So in this way, the configurations will be distributed according to this W of phi. What you have to do is you have to construct a way how to change this phi 1 configuration to the phi 2 configuration. So you have to construct a process or a transition probability to get from one field configuration phi to another field configuration phi prime, where this probability should be such that if you sum over all possible field configurations, this probability to go from phi to phi prime is equal to 1. Okay. And then, if you have this transition probability, then if you look into W of phi times P of phi to phi prime, and you sum over all possible field configurations, then you get another distribution, phi prime of W prime of phi. Okay. But what we need is that this W prime of phi is equal to W of phi. Okay? So we always want to have one distribution, W of phi, that we want to reach at the end. And this means that we need a fixed point of this Markov process. Okay. So that's one important thing of a Markov process, to have a fixed point which gives you the correct distribution. And then the other important thing too is that the probability to get from one field configuration to another field configuration is non-zero, larger than 0 for all phi and phi prime, and that is called ergodicity, because this means that no matter from which field configuration you start, you have a finite probability to get to any other field configuration. And that's very, very important. Okay. And if one has these two, so this ergodicity, and what else do we need? The probability, the transition probability here is normalized, then one can prove, and the proof is not too complicated, that a unique fixed point exists and that independent of the start configuration, the distribution converges to the fixed point. Okay. So at least if you make this n, where is it? Well, if you make this n here, so if you go to the infinite number of steps in your Markov chain, then you should reach a fixed point, so then your distribution, the field configurations should really be distributed according to this dimension. Okay. So this means that if you take the limit n to infinity of this transition probability p to the power of n times some initial distribution of your field configurations, and in this limit you get the correct distribution done. Okay. Then of course the question is, how can we construct a process which really gives us the distribution that we want? So remember, we want to have a distribution of the fields W of phi, which is given by 1 over z times e to the minus our action s of phi. So far this didn't enter in any of these steps here, so we have to find a way that we really get this distribution at the end. And one way to do this, which is the basic of almost all Monte Carlo algorithms, is called detailed balance. So that's a sufficient concept, but it's not necessary. Condition. But if you have this detailed balance, then you can prove that you get the correct distribution. And what does detailed balance means? This means that e to the power of minus s of phi times the probability times the transition probability to go from phi to some other field configuration phi prime is equal to e to the minus s of phi prime times the transition probability to go from phi prime to phi. Okay? So if you go somehow the opposite direction in your Markov chain, so not from phi to phi prime, but from phi prime to phi, then this probability should be weighted according to the action e to the minus s. Okay. And what doesn't enter here is the partition function. So in principle you have 1 over z here in front of e to the minus s, but you have it on both sides, so it cancels out. So this here you can calculate. So if you have a field configuration phi, you can calculate the action, and you calculate e to the minus the action, and then using some transition probability, you can assure, or you have to assure, that you have detailed balance. And then you can prove that what you get at the end, your, let's say, equilibrium distribution of the phi, they are then distributed according to that what you want, 1 over z times e to the minus s of phi. And that you can prove, and that's very important. Okay. Any questions so far? Yes?
Is it known how quickly this equilibrium is approached?
Well, that depends. That depends how you construct this transition probability. So how you really change your configurations. And that's much different for different Monte Carlo algorithms. So some algorithms have a very fast convergence, one has a very slow convergence. But that one can analyze for the end, or even argue for the algorithms. What you do there is you look into correlations or autocorrelations between subsequent configurations, or even configurations which are far apart, and calculate how they are correlated. Okay. And then you see that some algorithms are better than others. So how much time do I have left?
10 minutes.
10 minutes?
10 minutes.
Okay, then I can, I guess, finish with this. So now we know how to construct such a Markov chain, and we are then sure that it gives us the correct distribution of the field configurations at the end. But what we have to do now is to construct a way to get from one configuration to the other with this correct detailed balance condition. And I cannot explain all algorithms in detail, especially not for SU3, where it becomes sometimes a bit tricky. But I will just mention 3 of them. So the first algorithm, well, the simplest algorithm is the Metropolis algorithm. I will not go into the details here, because that has a very bad convergence to this equilibrium. So the heat bath algorithm, that is one algorithm which is also used in the program that I will give you. The idea here is to make local updates. So remember, we have this lattice, and we have the gauge fields sitting on these links between lattice sides. Say here ux, mu, which is an element at SU3. And the idea of the heat bath is to make local updates so just change a single link. So that's then one heat bath update. You just change this single link here. And you want to have that this link is distributed according to its surrounding, according to the local probability defined by the surrounding stable. Stable means here that if we want to make an update of this link here, then the stable are the links in this plaquette which do not contain this link, so we make an update here. So this here is the U, and the product of these 3 links here that is usually called stable. Okay. And we just want to look locally and want to bring this link here into a local equilibrium with respect to this stable here, and also the staple which goes down here, because that also is contained in the action. Okay. So what we need is, we need a probability for getting a u, and this is du times e to the power of beta over number of colors times the real part of the trace of u times a, where a is the stable. And the u here is the integration measure, the hard integration measure for SU3. Okay, so that's the idea. How this practically works, I cannot explain here in detail. It's not that difficult, and you can have a look into the code that I give you and maybe find out how it works for SU3. So that's one update. So the problem is you make only local updates, so you make very small changes in the field configuration. Of course you have to do this subsequently for all other links, but still you see large correlations between different configurations you generate in such a process. And that brings me to the second algorithm, which just takes me 2 or 3 minutes. That is called over-relaxation. And the idea here is to somehow decorrelate different configurations, again by changing a single gauge field u, but you change it as much as possible you want to bring it far away from the original link u without changing the action. This is rather simple. You just take u and build a new u prime, which is given by some matrix u dagger times the original link u dagger times v dagger. And then you have to choose a v in such a way that you don't change the action. In SU2, this is very simple. There you can just choose v equal to the staple divided by the square root of the determinant of the staple. And then it's easy to show that this new u prime doesn't change the action. In SU3, this is a bit more complicated. There you have to use an embedding of the SU3 in the SU3, but it's somehow the same way. Just maybe one word, but maybe one question to the students. What do you think is the problem using this over-relaxation? So you remember you don't change the action, so the action of this u is the same as the action of u prime. So what is the problem with this over-relaxation method when you think of what we need for a good definition of a Markov chain?
Okay, so that was the question. What about the answer?
Maybe you can think about that. So we should put this, the exercise online. I think I have explained more or less what is done in this program. So this program contains the heat bath and over-relaxation. These two are combined because they are needed to combine, as you will see when you answer my question. This program then calculates packet expectation value, packet values for subsequent configurations and also Polyakov loops. So you can take a look into this program You may have a look into this paper here, because there you will find values for the critical coupling, where you get the critical temperature. And then you can choose values close, for beta close to the critical one, and make some runs and see what happens. And maybe you can try to find the critical temperature using the simulations. You should use a rather small lattice of NT equal 4 and maybe spatial lattice of 8 to the power 3, so then you can just run it on your okay. What you need is an input file for this program, so you start your program like this. But I think this input file is easy to understand, so it's mainly the lattice size, the beta value, and then some output files. And the number of updates is written here. Okay, thank you very much.
Okay, thank you.